Hello everyone. Okay, so in this video we are looking at general trig equations. So like one of the last videos we were looking at simple trig equations where we were only finding two possible values for a angle in a trig ratio if our domain was between 0 and 360. Now we're looking at what if our domain was bigger than 360, or what if we have a coefficient that is in front of my angle within the trig ratio, and how we can solve for all the values of them. So if we go up now here to GeoGebra, right, so we're in GeoGebra now. So this is my unit circle, if you remember here. So remember, we recall every point on the unit circle can be written as cosine my reference angle and sine my reference angle, where cosine reference angle is my x-coordinate and sine of my reference angle is my y-coordinate. So the special thing about the unit circle is, so if I just show you here right now, let me put in alpha is equal to, let's say, 60. There it is. Alpha is equal to 60. So my value is up here. Now, what do we call, if we add on the periods, remember the period is a value for which it will bring me right back to where I started on the unit circle. So if I add 360 to this, so if I add 360 to this, I should be getting to 420. So if I add on 360 now, we'll see it's traveling around the unit circle. Ding, 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 ding. Traveling, traveling, traveling. Travel, travel, travel. Traveling back around. Bing, bing, bing. Getting up to 420 and 420. There we are. And now we're back to where we started, right? I can do this an infinite number of times. What if I add another 360 degrees on? So let me just see if I can change the color of this now. Let's see if we can change it to a red or something, right? Let's add on another 360 degrees. So 420 plus 360 is 780. So I'm gonna go up to 780 now. So I'm making my travels around. I'm gonna be traveling 360 degrees around. Ding, 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 ding. So 700 and ding, 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 ding. 80, and I'm back officially to where I started. So I can keep doing this and doing this and doing this. An infinite number of solutions I could have for this equation. So that's what's special about trig ratios. Now, a problem occurs if I have a coefficient in front of my angle. Now, I'm doing this live, so let's hope this works. So let me get rid of my trace here, clear all traces, gorge. Let me put in, so let me get this back to 0. Let me get rid of all my traces. Right, so I'm going to change this to 2 theta and sine to 2 theta. So now what I'm doing is I'm doubling my reference angle. So now my circle should be traveling around the unit circle faster, right? So let's look. I'm putting a coefficient out in front of my angle here. Let's see how long it takes me to get back to my original point here. Let's see. So I'm gonna go around and round 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 and go. And if you look here, $180. So now my period has been halved, right? So my function now is going around my circle faster. So we can nearly call this a rotation, right? The coefficient from the alpha here, we can nearly call that a rotation, i.e. how many times it can make its way around a unit circle within 360 degrees. So we can see here we looped around it once, and then I can see I can loop around it again. 360. So I traveled around the unit circle twice now within 360. That's because of this little guy in here. So these little coefficients in front of my angle really open the doors now for how many solutions a trig equation could have, because the bigger this number is, the more rotations I could have in my unit circle and the more possible solutions I could have for my angle. So let's go how to solve these now. So how to solve a general trig equation. So we've considered trig equations within a given domain, right? However, there are an infinite number of solutions like I show now. I can keep adding 360 or my period to a trig function, and I can keep doing that and keep doing that and keep doing that for as ever long as I want. So we need something called a general solution. So to find additional solutions, we take our original solution and add the period of the function, sine, cosine, or tan. So we have, say, sine x here and cosine x. The general solution is just x plus n 360, where 360 is the period. Right? If we're dealing with radians, we're adding n to pi. In this case, we're just going to be dealing with degrees, so we're going to be adding n 360. So what does that mean? Right? I keep adding on values of n, right? Or kind of like rotations, if you will, right? I can keep adding on values until I've reached all the values within my given domain. We're going to see now in a second, right? Cosine, my general solution is x plus n 360 because the general period of just cosine x, no 2x or 3x or anything, the general period of a cosine x is just 360. Then tan, the period of a tan function, however, is 180. So we have to be very careful if we're dealing with a tan function because we have to add n180 to it instead of n360. So how do we solve a general trig equation? So we calculate the two solutions as normal. So watch my previous video if you're unfamiliar with that. Then we rewrite the general solution by adding on the n period. So we find a general solution and then we get the angle on its own. And then we start with n is 0. And then we add n is 1, n is 2, n is 3. We keep doing that until all of my solutions are within my given domain. So let's have a look at an example here. Find all the values for x for which sine 3x equals root 3 over 2, where x is between 0 and 360. So this is a 2015 Leaving Cert paper, exam. This came in paper 2, question 5. So where x is in degrees. So your first step is you need to find out which quadrant in my unit circle this solution lies. So remember sex and the city. So sine here is positive. So since sine is positive, it's going to be in my first quadrant and my second quadrant. Done. Second one, right? But now we find my reference angle. So sine of my so sine my reference angle is equal to root 3 over 2. Or my reference angle is going to be sine inverse root 3 over 2. Or is equal to 60 degrees. So that's my reference angle. Next step, let's find my two solutions here. So I know I'm in the first quadrant and the second quadrant. So if you recall, in the first quadrant, we just leave my reference angle as it is. My second quadrant, it's 180 minus my reference angle. Third quadrant, 180 plus my reference angle. And then finally, 360 minus my reference angle if it's in the fourth quadrant. So I am in the first and I'm in the second quadrant. Now I find my two general solutions. So my first solution is just going to be 60 degrees. So remember, my or now is equal to this 3x. So I say 3x is equal to 60, and I add on my period, which is plus n360. I need to get x on its own, so divide every term by 3. So I'm going to get x is equal to 20 plus n 120. And I do that now for my other solution, so or 2. So my second one is 180 minus my reference angle. So 180 minus 60 is equal to 120. So I have 3x is equal to 120 plus n 360. Divide every term by 3. I'm going to have x is equal to 40 plus n 120. So I now have my two general solutions, and what I do now is I want to find all the solutions for x between 0 and 360. So what I like to do is, usually a rule of thumb is, right, usually a rule of thumb is, if I have 3x here, I usually do the first 3 rotations. So 0, 1, 2. So n is 0, n is 1, n is 2. That's the general rule of thumb. Now, it's a rule of thumb. It's not a concrete thing, because they could widen the domain really big. You'll see what I mean now in a second. So let's write up my general solution. So I have x equals, so I have 20 plus n 120. And 40 plus n 120. So I have n is equal to 0. When I sub in n is 0, 20 plus 0 times 120 is just 20. Then 40 plus 0 times 120 is just 40. So I have my first two solutions there. My second two solutions, n is 1. So 20 plus 1 times 120 is going to be 20 plus 120 is 140. Then 40 plus 120 is 160. Okay, so remember my cap is, my range is, my domain is from 0 to 360. So I'm still within 360, so I can add another rotation here. So n is equal to 2. So 20 plus 2 times 120 is 20 plus 240, which is going to be 260 degrees. Then 40 plus n120, so 40 times 2 times 240. So 40 plus 2 times 120, so 40 plus 240 is 280, right? And look what happened now if I add in another kind of rotation here. 20 plus 3 times 120, that's 20 plus 360, which is 380. 40 plus 3 times 120, that's going to be 400. So if you recall here, my domain is between 0 and 360. So my solutions are, for x, are 20, 40, 140, 160, 260, and 280. There are all my solutions there. And if you put this in your calculator, so if you open up your calculator now, hopefully I can. So if you put these in your calculator, so if you say sine 3 times 20, you'll see you should get root 3 over 2. This will load. Right. And my calculator is here. Right. So, my calc is in radians. I have to make sure it's in degrees. So shift setup. Oh, it's just menu. Sorry, is it? Nope. It's shift setup. There we go. Angle unit. I'm working in degrees. So if I put in sine 3, because my original function was sine 3x, sine 320, I get root 3 over 2, which is what the function is equal to. Let me try 3 times 40, root 3 over 2. 3 times 140, root 3 over 2. 160, etc. You get the gist. All of these are going to work, right? So one you just need to look out for is tan, right? Well, tan. Let's have a look here. So find the solutions of tan 3 theta equals 1. So what we need to do is, first of all, we need to find out where tan is positive, because tan 3 theta is positive. So it's going to be in the first and the fourth quadrant. Gorge. We then ignore the sign to find the reference angle. So tan or is equal to 1, or is equal to 45. Gorgeous. I now know tan is in the first and the third quadrant. So my first quadrant is going to be 45, so leave that alone. And then my third quadrant is going to be 180 plus 45, which is 225. So it's very important to remember the period for tan is 180. So I have my two general solutions here. 3 theta equals 45 plus n times 180. Divide everything by 3, I get 15 plus n times 60. 3 theta is equal to 225 plus n times 180, which is 75 plus n times 60. And then you're going to find your general solution. So you're going to put in values now. So I'm working with between 0 and 360. My apologies. It's going down. Right. And 360. So I find my solution. So for n is 1 first, I get 15 and 75. Then when n is equal to 1, so n is equal to 0, I get 15 and 75. When n is 1, I get 75 and 135. When n is 2, I get 135 and 195. When n is 3, 195 and 255. When n is 4, I get 255 and 315. And then finally, when n is equal to 5, I get 315 and I get 375. So if you recall, I'm working between the domains 0 and 360, so it's going to be this solution, this solution. I don't need to repeat solutions, right? So 1575, 135, 195, 255, and 315. And they are all of my solutions there. Then finally, I'll look at this one more example here, 2.2. So I have cos 3 theta is equal to minus 1 over root 2, where my domain is 0 to 2 pi. Right, 0 to 2 pi. So I'm now dealing with radians. For me, I just like working with degrees and then convert them into radians at the end. Because I find with radians, you're working with such like awful fractions. I just like work with degrees, convert at the end. So cosine cosine 3x equals minus 1 over root 2. So that means it's in quadrant 2 and quadrant 3. Because cosine's negative here and cosine's negative there. Ignore the sign and find the reference angle. So we drop the minus and then we find the reference angle. So cosine 1 over root 2. So again, for me, I like dealing with degrees and then deal with radians at the end. So I have my angle is equal to 45 degrees. Now, if you were brave enough to work in radians, you need to change this part. If you were working with radians, your reference angle here will stay the same. This 180, no, that'll have to change to pi because we're dealing with radians. Same here, and this would be equal to 2 pi. So if we were dealing with radians to find my two initial solutions, the second quadrant would be pi minus the reference angle and pi plus the reference angle, but I'm not doing that. So I'm leaving them in degrees. So my two solutions are going to be 180 minus 45, which is 135, and then 180 plus 45, which is 225. So my first solution is going to be 3 theta equals 135 plus n 360. N360 because N360, so 3 theta equals 135 plus N360 because the period of a initial cosine graph is 360. Divide everything by 3, so 135 divided by 3 is 45. So I get 45 plus N120 is my first kind of general solution. Then my second general solution is going to be 3 theta equals 235 plus N360. Divide everything by 3. So, 225. 225 divided by 3 is 75. So we get theta equals to 75 plus N120. And there's my second general solution. Now we sub in for values of n. So when n is 0, I get 45 and 75. When n is 1, I get 165 and 195. N is 3, I get 285 and 315. And when n is 3, I get 405 and 435. So they are my solutions. So remember, my domain is 0 to 2 pi, which is 360 degrees. So first of all my solutions are 45, 45, 75, 165, 195, 285, 315. 4 or 5 out of my domain, we don't count it. And then to convert to radians, I multiply by pi over 180. So I multiply everything by pi over 180, and then I get all these solutions here. I would do them out for you, but I hate fractions. See what I mean? All these like nasty fractions I'm dealing with now. So I multiply every one of these by pi over 180. 45 times pi over 180 is quarter pi. 75 times pi over 180 is 5 pi over 12. Imagine working with 5 pi over 12, right? 165 times pi over 80, 11 pi over 12, etc., etc. So make sure to always include your answers in the relevant units. Right, let's look at just a few more examples, just kind of like fun, tricky ones. Right, so it's this example here that's asking us now. So instead of multiplying the angle within my graph, we are actually dividing. So sorry, it's being a bit temperamental on me now. Right, there we go. So this is from the 2020 paper. Find two values for theta for which tan theta over 2 is equal to minus 1 over root 3. So again, sex and the city. Find the two regions it's in. Well, tan is negative, so it's going to be in my second and my fourth quadrant. Find my reference angle. So tan, my reference angle, is equal to minus 1 over root 3. Remember, we drop the sign. So my reference angle is equal to tan inverse 1 over root 3. Which is my reference angle is equal to 30 degrees. Next step, I need to find my two solutions now, my two initial solutions. So my reference angle 180 minus my reference angle 180 plus my reference angle and 360 minus my reference angle. So I'm in quadrant 2 and in quadrant 3. So my first angle is going to be 180 minus 30, which is 150. So I'm going to have theta over 2 is equal to 150 plus, and I'm dealing with tan. I'm dealing with tan now, remember? So it's going to be N180. Multiply everything by 2, I get theta is equal to 300 plus N360. That's my first solution, my first general solution. My second general solution is going to be 360 minus 30, which is 330. So it's going to be theta over 2 equals 330 plus N180. Multiply everything by 2. I'm going to get theta is equal to 660 plus N360. And there's my second general solution. So let's look at my domain here. So between 0 and 4 pi. So that's going to be between 0 and 720 degrees. So I'm dealing between 0 and 720. Now remember, we're going to have to convert to radians in the end. So let's find my two solutions first. Right. So I'm going to have 300 plus N360, and then under here 660 plus N360. So I'm going to have N is 0 here. When N is 0, I'm going to get 300 degrees here, and I'm going to get 660. When N is equal to 1, I'm going to get 300 plus 1 times 360, which is just 660. And then 360 plus 1 times 360 is just going to be 1020. And I'm already out of my range. So my two solutions are going to be 300 and 660, because remember my range, my domain is between 0 and 4 pi, or 720. And then finally, my solutions, I have to convert to radians. So theta is equal to 300 and 660. So multiply by pi over 180. So 5 over 3 pi and 11 over 3 pi. They are my two solutions to that question, right? And the final one I want to show you here is a fun one, right? So this is one of the 2009 papers, this is ages ago. Find all the solutions to the equation cosine squared x minus cosine x equals 0, where x is between 0 and 180, right? So this is fun. Well, I have a cosine squared here and a cosine x here. What am I meant to do? This is kind of a quadratic. But I notice here, let me factor out cosine x first. So if I factor out a cosine x, I'm going to have to take my bracket. Cosine x minus 1 equals 0. So I have two factors equal 0. So a times b equals 0. Therefore, a equals b, or, sorry, a equals 0 or b equals 0. So therefore, I'm going to have cosine x equals 0, or I'm going to have cosine x minus 1 equals 0. So I'm dealing with here between 0 and 180. So I actually don't need to deal with my general solution here, because my general solution won't give me any more solutions here because my domain is so small. So I just need to inverse these like normal. So x is going to be equal to cosine inverse 0. X is going to be equal to 90 degrees. And then here, I'm going to have cosine x equals 1. Cosine x equals 1. X is going to be equal to cosine inverse 1. So if you can kind of recall here on my unit circle, right? This is why I'm saying it doesn't really matter. If you recall here on my unit circle, actually, we can come back to this example now in a second as well. Actually, we don't need to come back to this example in a second. Right. So remember here, cosine is my x value. So I'm looking for where cosine is here. So it's here when my reference angle is 0, but it's also back here when my reference angle is equal to 360 because I did full rotation and back here. But my domain is only up to 180. So I actually only need the first one here, which is x is equal to 0 degrees. That's the same for over here, right? So I'm dealing with x, cosine x is equal to 0. Oh, so this is cosine is equal to, yeah, cosine is 1. Cosine is equal to 0. That only happens here, or it happens here, right? So that happens at 90 degrees, and then it happens again at 270. But again, my domain is between 0 and 180, so I just need the 90 degrees. So my answer to this question is 0 and 90 degrees. So make sure to always double check your answers on your calculator. How fun is this? So cosine 0 squared, I'm just double checking my answers. Cosine 0 is equal to 0, gorgeous, and then 90, 0, right? So double check my answers, I'm very happy with them, and that's it. And that was a long one, but did a load of examples there. I hope there's some help to you, and I'll catch you guys later. Bye.